Okay. Um, Good evening to problem solving session for week 11 of computational complexity. My name is Bhavya. Okay. And so we are nearing the end of this course. So there are a total of 12 weeks and we are in the 11th week. So it's almost over. Before moving on to the details, I would like to make one announcement. And that announcement is that okay, week 11 right now is happening on 8th October, right? So, and week 12 will similarly happen on one moment. Yeah. Week 12 will similarly happen on 15th October. All right. So, again, the normal session. So, I'll be holding a brief. Okay. I'll be holding a 1 hour extra session on 16th October. 16th October, and this will be a Wednesday. Okay, this is Tuesday, and this is Tuesday. So, okay, 16th of October I'll be holding, but it will not be at 6 p.m. It will be at 4 p.m. 4 p.m. to 5 p.m. So, here I plan to discuss quick summary. If you are registered for the exam, then this may help you once for a quick summary, and we may clear some doubt clearing, if any. And finally, I want to cover some portions which are sort of like at the frontiers of complexity theory. So, current research in complexity theory. What is known right now, and what are people trying? What are the hot topics right now in complexity theory? So that is what I want to tackle. Okay, during this extra session. So, okay, take note of this, and so if possible, please attend this extra session. It may prove helpful to you. Okay, so that was all in the announcement. So let us move on to the details. Okay. So the topic for this week is communication complexity. Now, this is an entirely different model. Okay. Uh, of But this is a very powerful model. Okay, and what is communication complexity? So it was introduced by Yao around in the 80s or something. Okay, he was introduced by Yao, a prominent complexity theorist again. So in the 1980s, talking about if there are two parties or three parties, whatever, and how do you quantify the complexity of that particular setting in terms of communication? So, but there were previous attempts, okay, to think about this, but Yao was the first person who formalized it and then brought it down to the simplest possible setting where it still makes sense to study the complexity of communication. Okay, so we've studied the decision, right? We've studied non-determinism, and we've studied counting. Now we are talking about communication. So what is communication simply? Okay. Now what is communication complexity? What is a model? The model of communication complexity, or the communication complexity model, is that there are two parties. Okay. Okay. Two parties, and they are Alice and Bob, commonly called Alice and Bob. Okay. You'll hear Alice and Bob in, say, communication complexity or distributive computing or cryptography, whatever. This is a popular name choice. And Alice and Bob, and there is uh, and there is a function f. Okay, the function is not a single input function, it takes two inputs. Okay, it takes two 0 to the 1 to the m, 0 1 to the n, and the maps it to a single bit. Okay, so you can generalize this to multi output functions also, but for the simplicity case we'll assume it's a boolean function. And you have Alice and Bob, and they each have some input x, which is in 0 1 to the m, and Bob has another input 0 1 to the m. Okay, now Alice and Bob, they need to communicate, they need to compute the function f. This function f, compute f of x comma y. That is what it needs to do. And Alice and Bob are all powerful. Okay, what do you mean by all powerful? That is the amount of time that Alice takes on her side and the amount of time that Bob takes on his side, okay, or space or time, whatever they take on their sides, is not taken into account. Okay, so the only thing that matters is how much of communication is happening to them, taking place. Okay, so now Alice sends some bits and Bob sends some bits, and then Alice sends some other bits, okay, and so on. Okay, so this is what is called a protocol. A protocol is a transcript. It is a record of who sends what bits where. Okay, and until the problem is solved, that is, they know at this point one of them knows what is f of x comma y, and then it is either 0 or 1, and then that is communicated to Bob. Okay, and because what do you mean by computing f of x comma y? It means that both Alice and Bob should be informed at the end of what is the evaluation of f on x and y. Okay, it is not enough to just do this. It is not enough only for Alice to know the output. Bob should also know the output, but you know the overhead is only plus 1 bit that way. Okay, and so the communication complexity of pi, which is also shown by d of pi or cc of pi. Okay, d stands for deterministic, cc of pi is equal to, okay, number of bits exchanged by Alice and Bob during protocol pi. Okay, so this is an example, and one example is, for example, Alice has x, Bob has y. Okay, f, okay, is f of xy is 1 if x equals y, 0 otherwise. Okay, so you have Alice here, you have Bob here, and you have x here, you have y here. And now what is a possible protocol for this? What is an this communication protocol to do this? Solve f of x comma y. Both are say n bits. Yes, Suraj, any idea? And basically they want, yeah, they want to check
Uh,
whether it's equal or not. Yeah.
n plus 1.
Yeah, but how is that n plus 1 coming? What is the actual protocol?
Sir, Alice can send x to means n bits to y, and just
Right.
y will give one bit to x in
Right.
the
Yeah.
output.
Right. Good. So Alice will send all x, entire x, to y, okay, and which is n bits. And Bob says, okay, let's see, x equals y. He compares it, and he says no. So then he needs to send, say, a 0. So this is the protocol, right? And another one, let's say Alice, Bob, okay, and one has x, the other has y, and what is the function? Um, okay, yeah, let's do parity only. F is nothing but um, x parity y, okay, or something like parity of x dot y. Okay, what I mean by this is, so x is composed of x1, x2, and so on, right? Xn parity, XOR simply y1 parity y2 parity y3, and so on till yn. Okay, so in other words, so it will, f in other words will give a 1 if xy has odd number of ones, odd number of ones, 0 otherwise if it has even number of ones, if xy when concatenated together. So what is the possible protocol for this? Any idea? I'll give you an example. Okay, for example, Alice has 0 1 1 0 1, and Bob has 1 1 0 1 0. Okay, 1 1. Okay, so Alice has this and Bob has this. This is x and this is y. Okay, so what is x? What is xy? Is 0 1 1 0 1 and 1 1 1 1 0 1 1. Okay, and now count the number of ones. Count the number of ones. 1 2 3 4 5 6 7. So f of xy is equal to 1. Why? Because number of ones in xy is odd. Okay, so this should be the output. This is the example I'm giving you. So what could be a possible way to do it? Okay, first, will the same strategy work here? Sending all x bits.
Yes, sir.
Yeah, right. So you can always send x bits, and then Bob will check this. He'll do this computation on his side, and like I said, among themselves, if they do within themselves, if they do any computation, we'll not charge them for it. Okay, we won't consider their time complexity, space complexity, whatever. Okay, and it could send X bits that side, and oh, okay, then it does this thing, and then realizes that, oh, okay, XY is odd, and then it sends back 1 bit. Okay, so again, n plus 1 many bits. Okay, so we can do it for any function. We can do this procedure for any function. Okay, we can do this procedure for any function. We can do this procedure for any function. So we have that for any function f, okay. Okay, let's for simplicity, let's say this is n. Okay, deterministic communication complexity of f is at most, we are upper bounding. Okay, oh, okay, I did not talk about it, but okay, I'll come to it. Okay, n+1 right now. What I just mean is that you can always build a protocol that takes n+1, whose communication complexity bits is communication complexity is n+1. Okay, because you just send all of the inputs one side. Okay, and can you come up with a better protocol here for this parity case?
X can compute the bit, I means XOR, and then he will send the result to Y. So it will take 2 bits.
Exactly. Right. Good. So what Alice does is, okay, she computes parity X. Okay. Right. XOR. And then this is equal to B. So B says whether X already has even number of ones or not, or odd number of ones or not. So it sends B over to Bob. B is a single bit. Okay. Now Bob looks at this guy, this bit. Okay. And then what it does is Bob does B parity Y. Okay. So not B parity Y, B parity of Y. B parity parity of Y. Okay. Number of ones in Y. And if this, let me call it B prime, and then he replies this B prime. Good, right? So you can try it with this example and then verify it. And so what do we have? That this guy parity, okay, the communication complexity of parity is at most 2. So now the question is, can we improve it? These are the kind of questions that we can ask. Can we improve it? For example, equality, can we improve it? Equality, we already know this, right? Using n+1, we can always create. Can we improve it? That is the question, right? Now, can we improve DF? Or if you want to say that you cannot improve any further from this, okay, you make use of lower bounds. That is, show that DF is at least some K. Okay, let me say G. Okay, no, K is fine. D of F is at least some K. This means that the best communication complexity protocol you have cannot be less than K. Because what is D of F? D of F is taking the best protocol, okay, best protocol out of all the protocols. Takes the best protocol and for that protocol it takes the uh, min of the size of the protocol. You can say the worst case size, but it's fine. Min of the worst case size such that pi solves f. Okay, and anyway, we use lower bounds this way. Okay, so until what point can you improve? That is what lower bounds do. And take note that lower bounds are much more difficult to prove than upper bounds. You may have already seen it in circuit complexity. For example, we don't know any better lower bound than linear little o of n. Okay, so lower bounds are an attack method to separate circuit classes or complexity classes P and NP and so on. And we use lower bounds to do this here. Okay, can you do better and not and so on? For example, equality, you can provably show, you can show that d of f is at least n plus 1. D of equality, okay, is at least n plus 1, which means d of equality is also at most n plus 1, trivially. So d of eq is exactly equal to n plus 1. You cannot transmit smaller number of bits to actually so this lower bound is tight in other sense. Okay, now now okay, we have some motivation for lower bound. Okay, we have some motivation for lower bound. Let's see. Um, yeah, okay. Now I'll just quickly mention some important things. Okay, uh, we may have seen it in the lectures what a protocol tree is. Okay, a protocol tree is how your protocol behaves. For example, you have Alice here. Okay, Alice asks what is x1. Okay, and x equals x1, x2, and so on till xn, and y equals y1, y2, and so on till yn. Okay, Alice asks what is x1. Let's say the Alice sends x1s, and Bob sees that, oh, okay, x1 is 0, so what should I send next? Or it may be that Alice is sending multiple bits. Okay, in that case it will look something like this. Alice sends 1, then Alice again sends a 0 or 1, whatever. Okay, and this is, let's say, x2 and this is y2. Point is, it may not be Alice sends and Bob sends, then Alice sends, Bob sends. Okay, but for simplicity's sake we can always assume that it's Alice Bob and so on. Okay, so now Bob looks at x1 and says, oh, okay, so she revealed this x1 bit, so let me reveal the y2 bit. Okay, and Bob could have replied that, okay, y2 is 0 or y2 is 1, but Bob never lies, Alice also never lies. Okay, now if Bob said that, okay, y2 is 0, now Alice is again like, oh, okay, then let me reveal my x3, and then she gives 0, 1, and so on. And here again, Alice, if Bob had said y2 is 1, then Alice is not interested in x3, she's interested in x4. Okay, and she sends either a 0 or 1 depending on what x4 is. Okay, now this is how it goes. Now we have this is called the protocol tree. Now we want this idea of what is called a communication matrix, which is a very strong notion. Okay, so what is communication matrix? It's nothing but evaluation of f on x and y. Okay, so so what does it look like? So this is possible values of x, all possible values of x. and here all possible values of y. Okay, so here there is 0 to the n, say, and this is 0 to the n minus 1 1, and so on till 1 to the n, all possible values of x. Okay, let this be y actually, y and all possible values of x could be 0 to the n, 0 to the n minus 1 1, and so on till 1 to the n. So what is the dimension of the matrix? How many rows, how many columns? So you have 0 to the, I mean, it's all possible values of x. Okay, and x is an n bit number, right? N bit string. So how many strings of n bit length? Yeah, okay. 2 per n cross 2 per n. Correct. That's right. Good. So this is 2 per n. This is 2 per n. Now, what you do is, for a particular x, for a particular x and y, okay, you evaluate f. Okay. Now, so you start filling this. And so on. So this matrix is filled with zeros and ones. Well, this is nothing but actually a truth table, okay? But this is like a two-dimensional truth table because there are two inputs. Okay. Now, so it computes f of x, y across all possible values of x and y. Now, let's say Alice is holding one copy of this matrix and Bob is also holding one copy of this matrix. Okay. As soon as Alice says that her x1 is 0, as soon as Alice says her x1 is 0, then there are so many entries out here that is not useful for us. That is when x1 is 1. So let's say Alice said x1 is 0. Okay, let's say Alice said x1 is 0. Then what do you have? That we only require those values where the first bit is 0, right? So all the values which have first bit as 1, okay, which will be several matrices. Here 1 1, here will be something 1 followed by something, 1 followed by something, 1 followed by something, and so on. All of these are struck off. We don't need it. Okay, and then Bob says his y2 is 1. Okay, Bob says his y2 is 1. Okay, actually color the screen. Okay, Bob says his y2 is 1. Now if Bob says y2 is 1, remove all those rows which have y2 equals 0. So oh no, okay, I removed at y's side, sorry. So 1 1 1 and strike off all these rows. And Bob has y equals 1, so strike off all the y2 is equal to 1. So let's say it's something like this. You don't need it. And then as they reveal more and more information, this place gets smaller and smaller. So what is actually happening is, okay, you get what are called rectangles. Okay, at this point, okay, at exactly this point, okay, you know what at exactly this point you have already queried x, and at this point you've already queried y, and then you get what are called rectangles. Okay, and okay, so I won't delve too much deep into it. I think I've gone too deep into it. So you get these rectangles which are associated with each node. Okay, it could be like this, it could be like this. Okay, it could be like this. Okay, and I'll quickly define the rectangle. Okay, a rectangle is nothing. Okay, so there are two definitions you can come up with. One is rectangle is nothing but a cross b, where a subset of x, b subset of y. And what is x and y? um, X, all possible values of small x, and y, all possible values of small y. Okay, so oh, okay, sorry. Sorry, not all possible values. X is nothing but x1 to xn, y is x2 to xn, or actually don't keep the x, it's confusing, 1 to n. Okay, so you take any subset from here. Okay, it will form a rectangle, and you may say something like, uh, I did something like 2 5 cross 1 2. Okay, so 1 2 would be somewhere here, and 2 5 would be somewhere here. Okay, so these points form a rectangle. 2 5 on exercise side and 1 2. Okay, now this forms a rectangle. You may say it does not look like a rectangle, you may say. Okay, no problem. It's only up to renaming. I can bring rows up and down, left and right, and then I can make it look like a rectangle. No problem. Okay, but again, you have these special kind of rectangles which are called monochromatic rectangles. Okay, so what are monochromatic rectangles? Monochromatic rectangles. Oh, okay, before, another definition of rectangle is if x comma y is in a cross b, and uh, x prime comma y prime is in a cross b again. Okay, then x comma y prime x prime comma y is in a cross b, then it is a rectangle, if and only if a cross b is a rectangle. This proof I want to. Okay, these are the two definitions of rectangle. What does it mean? It means if I have something like this. Okay, if I have 2 comma 5 and 1 comma 2. Okay, 2 comma 5 and 1 comma 2, then even 2 comma 2, which is here, belongs to the rectangle, and even 5 comma 1, 1 comma 5 belongs to the rectangle, which is here. Okay, actually it's 5 comma 1. 5 comma 1 belongs to the rectangle. Anyway, so this is there, but but now think of rectangles. Okay, but all of them are zeros or all of them are ones. Okay, inside the rectangle, these are what are called monochromatic rectangles. For example, let's say this is a rectangle, these are all zeros and these are all ones. Okay, sorry, ones. These are all ones. Okay. Now, um, these are what are called monochromatic rectangles. Okay. And okay, every leaf in the protocol tree corresponds to a monochromatic rectangle. Right. So we already said that at each node you are splitting the into rectangles, right? So there is some rectangle associated with this. That is the entire matrix. Now you make the rectangle smaller and smaller, and finally you will get your output, okay, here, which is 1. So and there is a rectangle associated with this. So it only makes sense that all of the outputs at that point is 1, right? So yeah, that is. But again, the proof I'm not doing. Okay. Now, okay, now that you have this, okay, there are two two points to note. Okay, I'll just write it here. Okay, so I'll call it a theorem. Okay, if any partition of x cross y into f monochromatic rectangle requires at least t rectangles, then d, this is the log deterministic communication complexity is at least log t. Take the communication matrix, okay, and try to partition it in every way possible. Let's say it is not possible to partition it into less than t rectangles, okay, then the communication complexity is at least log t, okay, and this is one way to prove a lower bound, one technique, okay, and okay, another thing I want to write is the rank lower bound, which is, okay, again another theorem, let's say, okay, which is for any, now again another very powerful theorem, f, okay, which maps from x cross y to 0 1, d of f is at least log of rank of the matrix, and let me call it mf. Okay, this is mf. Okay, so two very important theorems to prove lower bounds. Okay, first is what is called a rank, second is what is called a rank lower bound. You take the communication matrix, find out its rank. What is rank? Rank is the maximum number of linearly independent rows or columns, whatever. And you find the log of it, and actually one leads to the other. Okay, in this theorem, in these two theorems. Now, what is the first one? First one is you try to partition it into many rectangles. Let's say it requires at least 3 rectangles, then df is at least log t. Now we'll use both of them. We'll see examples. Okay, so let's begin. So okay, I'll duplicate this. Oh no, there's no use of duplicate. I'll copy it, paste it here, and I'll crop. So here's the first question, a simple question. Okay, let f be such that its communication matrix mf has distinct entries. Okay, you have some f and you compute mf. Okay, mf again, as I said, it is this 2 to the n cross 2 to the n matrix, right? And all the entries, but what it means by entries is rows, okay? Distinct rows. All the rows are distinct. Then show that d of f is at least log n. So how do we do this? All the rows are distinct.
If all the rows are distinct, means they means row must be start from like 000 to 1111 like this.
Okay. So okay, you mean 000 00001 like that 00010.
Yes, sir.
Okay.
They will be muted means 00 can go up or down, but
Okay.
overall we.
Okay. Okay. Let's see. Okay. So all of this, so they are all distinct. Okay. Continue. But so why is the
So we
communication complexity I?
we can make now n rectangles.
You can make n rectangles. Okay. Hmm. Okay. Okay. Let's see. um, okay. Good try. But there is one catch here. Okay. What is the dimension of this matrix?
2 की power n into 2 की power n.
Yeah, right. 2 to the n. 2 to the n. Right. Now, so each of these rows, each row is r, which is in 0, 1 to the 2 to the n. Okay, each row is of 2 to the n length. So it is a member of this set. Now, how large is this set? How large is this set? What is the size of this set? 0, 1 to the 2 to the n. Or in other words, how many 2 to the n length strings are there? Strings of length 2 to the n. How many strings of length 2 to the n are there?
2 की power 2 की power n.
Right. Answer is 2 to the 2 to the n. So many strings are there. Okay. And the height of this is how many rows are here? 2 to the n. And how many strings are of length 2 to the n? 2 to the 2 to the n. You get it, right? And so it cannot be that all of them feature in unique rows. All of the strings. Are you getting what I'm trying to say?
Yes, sir.
Right? So all 2 to the n length strings will not feature in this matrix. So something like this will not happen, where all possible entries are there. Of course, what will happen is from this 2 to the 2 to the n, you'll choose distinct 2 to the n elements. You'll choose some 2 to the n elements and then place it here. Okay, so all of them may not be here, but all of them are distinct and they are taken from this set. So yeah, okay. So I just wanted to address that particular approach. So now, but there is a simpler approach. Okay, to proving this. Okay, if all rows are distinct, Suraj. Okay, if all rows are distinct. Okay, 0, 1, 0, 1, 0, and 1, 0, 1, 0, 1, and so on. Okay, and they and by distinct that means no row is repeated. No row is ever repeated. Can you say something about the rank of this matrix?
Rank is 2 to power n.
Rank is to the power n. Correct. Good. Because we are working over F2, we are only working over zeros and ones. What do you mean when two rows are linearly dependent? We mean that they are exactly the same, right? If we were working over, let's say, reals or rationals or whatever, then we could have said that, okay, 2 4 and this row 2 4 and row 4 8 are linearly dependent because we are working over reals or something. But the fact that we are working over with just 0 and 1, okay, when you say two rows are linearly dependent, it means they are exactly the same, right? So what do you have? Rank of MF is what? Exactly equal to 2 to the n. Okay, rank of the matrix is exactly equal to 2 to the n. Okay, now what do you have? The rank lower bound is deterministic communication complexity is at least log of rank of MF. Okay, oh, okay, sorry, very sorry. Okay, this should be n. So, what was I? Yeah. So now by rank lower bound, deterministic communication complexity of F is at least log of rank of MF, which is equal to log of 2 to the n, which is equal to n. Okay. So if all the rows are distinct with each other, this is one method to obtain a lower bound. Okay, good. So let's look at another problem. Okay. I think first we need to copy it and paste it somewhere else. Okay, correct. Let's crop it. Okay, consider this problem. Sys. Okay, there is a graph G. There is a graph G. Okay, and Alice and Bob are each given two graphs. Okay, yeah, two sets actually. Alice is given a click. For Alice, there is a set of vertices which forms a click. So, what is a click? A click is a set of vertices which have where all of them are connected. Right. So Alice has a click. What does Bob have? Bob has an independent set. Bob has an independent set. So what is an independent set? Independent set is a set of vertices that don't share vertices with each other. Okay. What do you need to compute? Both of them need to figure out if f intersection I is equal to phi. Okay. That is, f is 1 if C intersection I is empty and 0 otherwise. Okay. So in the same graph, the graph is the same. Okay. They are given two sets of vertices. If the graph is the same, they are given two different sets of vertices. One is a click, we'll call it C, and one is an independent set, we'll call it I. Okay. Question is, does there exist a vertex which is shared among both of them or not. Does there exist a vertex V such that V is also here? Okay, so that is the question. Now, this requires a bit of thinking. Okay, this is not immediately obvious. I'm coming back in a second, but try to think about coming up with a protocol. It's asking for an upper bound, right? An upper bound means you come up with a protocol, come up with an algorithm. Lower bound means you prove that the protocol does not exist. Now, yeah, the hint is you need to do some kind of bind research. Okay, 2 minutes, 1 minute actually. Hi. Uh, yeah, any idea? Although this is not very simple, but any idea, Suraj?
Sir, what is n here?
Okay, good question. What is n here? So um, n you can take it to be the size of the graph. Anyway, because of the order notation, it won't be a problem. But n you can also take the number of vertices in the graph is also fine. Size of the graph is fine. Number of vertices is fine because we're not exactly talking about log square n. We are talking about uh, order log square n. So okay, okay. I'll give you one more minute. Okay, shall I tell?
Yes, sir.
Okay. So the idea is as follows. Okay, you want to do a binary search, okay, on the set. Okay, so binary search is not only on lists, arrays. Okay, you can do binary search in several structures. What you are doing is you are halving the set each time. Okay, now what you are doing is, okay, what you are doing is, if there is a vertex in common with both C and B, C and I, okay, then the degrees in the graph G will be the same, right? Because we are talking about the same vertex in the graph G. Okay, the degrees will be the same. That is the key idea. And now you're going to do a binary search on the degree. Okay, so what does Alice do first? Okay, Alice does this. Okay, does there exist a vertex V, okay, in C, okay, in the click C, such that the degree of V is at most n by 2 in G, in the original graph G, okay, is at most n by 2. So you have this V, okay, and what is it saying? Does V have at most n by 2 neighbors? Okay, does V have at most n by 2 neighbors? That is what it is asking. What would be, if no, then V has at least one neighbor which is from outside. No problem. Okay, but it asks this. Okay, if it exists. Okay, if yes. Okay, if yes, then what do you do? Then send V to Bob. Okay, send V to Bob. Okay, now what do you do? Not just send V to Bob. Actually, um, what you also do is you narrow down now. Okay, so new C, I'll call it C prime, okay, or Cn by 2, is now that particular click which has so just all the neighbors of V, which is usually shown by this, or I'll write capital N, NV. So all neighbors of V. Okay. Now, so why is this happening? So what you want to do is you want to narrow down to V, that particular vertex. Okay. Now you said, is there a V such that a degree is at most n by 2? And yes, there is a degree V such that degree is at most n by 2. You want to match that V with the V in the Bob side. Okay. You want in Bob side also what you want to do is you want to ask if there is a vertex with degree at most n by 2. Okay. What you want to do, because both the V are same, the degree will be the same. If such a V exists, okay, the degree will always be same. Where in the original graph, okay, yeah, sorry, I think I confused you by saying the degree will be same. The degree will be same in the original graph, okay, in within the click and within the click also it will be same, but within the independent set it won't be the same. Okay, but yeah, so I want to narrow down to this. So I'll check what is the degree. If let's say the degree is not, it is at most n by 2, okay, and I want Bob to narrow down to that, so I'll send Bob that V, okay. But what do I want to do? Since its degree is n by 2, I have an advantage now that I'll choose only n by 2 many of the the vertices it has, okay, and take it as my new set, new click, okay. It will form a smaller click, okay, and so we have that, right? Now what we do is, um, now we have that. Now we have reduced the size to half, essentially. So, but it is still a part of the click. Okay. So if it could be that V was pointing somewhere else. Okay, no problem. but we'll take all of V's neighbors. Okay, we was attached to someone outside the clique, no problem, but um, it is still fine because all everyone in the clique is still V's neighbor. Okay, why is this fine? Because C, okay, is a subset of n of V. C of n by 2. Sorry, C. That's fine. Right. So, no problem. Good. Now what we do, okay, so far we've not reduced yet. We've in fact possibly increased it. But when we do keep doing this process, it will decrease. Okay. Now what do we do? In Bob's side, Bob Bob got a vertex, okay. But now Bob asked the same question. Okay. Bob asked the same question. Um, does there exist vertex V in the independent set such that degree of V is at most n by 2? It wants to do the same thing, right? It wants to do the same thing, but since it has the independent set, it can ask it in a different way. It can ask um, such that neighbors of V, non-neighbors of V, is at most n by 2. What does it mean? This is equivalent to saying neighbors of V is um, not at most n by 2. Uh, just a moment. Um, at most n by 2, neighbors of V is greater than n by 2. Okay, sorry. Non-neighbors is at most n by 2. Non-neighbors is at most n by 2, which means neighbors is strictly greater than n by 2. Right. Cute. Okay. Okay. Um, to narrow down to this particular vertex, and you want to say that neighbors of V um, okay, so Bob would ask the opposite question. I mean, Bob would ask at least n by 2. So, yeah, that should fix it. Same thing. This is neighbors is at most. Okay, but yeah, it'll ask the same thing. Bob will ask the same thing, and uh, again he will update the set in his end. Okay, and what does it mean? Bob now has Bob now says, why is it asking non? Well, uh, there are. It is asking how many neighbors are there. Okay, or it is asking, are the neighbors non-neighbors greater than n by 2, which means, okay, are the neighbors at most n by 2. So we want to find an intersection between them that is the same degree. So we want the number of neighbors to match. But why did we ask this? Because now what we want to do is we want to take the non-neighbors and take it as a new set. Okay, if yes, okay, the new set I n by 2 is the all the non-neighbors of V. Okay, now all these people, belong to V, belong to the new set. Okay, and now the next time we do this process, okay, next time we do the process, that is when the process narrows down. Now we ask not for n by 2 but for n by 4. Is there lesser than n by 4 neighbors, degree vertex? Yeah, there may be. Let's say there is a smaller vertex n by 4, and now you do it on Bob's side also. Is there less than n by 4? And yes, there is. Let's say, then we try to match it. If not, then we go to 3n by 4, slightly above. But what you see here is you are doing sort of binary search. Now let's say both of them cannot. And by the way, if Alice is not able to find, then she'll send something like a bottom symbol. Okay, she'll send a bottom symbol. If no, send bottom. And if Bob doesn't find, then send bottom. Now, if both are not able to find, okay, and both the sets contain the independent set as well as a click, okay, and they are not able to find, right, that vertex of that particular degree, then there is a problem. They are not able to find vertex of that particular degree because there's no matching degree only. Okay, so where the neighborhood also matches. Okay, so we are also matching the neighborhood at the same time. And finally, I mean, the and another observation is that C intersection I is will finally either be exactly equal to 1 or exactly equal to 0. Why? Because if C intersection I is, let's say, equal to 2, it means there are two vertices which are in a clique as well as an independent set. But since it's in a clique, okay, it cannot be in an independent set because both cannot be in an independent set because this edge is shared between them. So you either have a 0 or 1 answer, and you keep doing this process. Okay, and this is just some kind of binary search, right, which takes log n levels, and at each level you are sending the vertex which is indexed by log n bits each. Okay, so binary search takes log n rounds. Okay, and each round has log n bits. Okay, so total log square n bits exchanged. So communication complexity of this particular problem, have I named it CIS? Okay, is at most log square n bits. Okay, that is the general idea. So Suraj, is it fine?
Yes, sir.
Okay. Okay, sure. Let's move on then. Okay, I need to do this copy business again. Maybe if I copy, paste that. Yeah, okay, good. So the third question. Okay. So, okay, so we saw the log rank technique to do it. We saw an upper bound technique. Upper bound technique is simply try to come up with a protocol, right? So, one technique that was talked about in the lectures, I believe, is what is called the fooling set technique. Okay, and this is an important technique. Okay, so what you do here is, just one moment, I'm going to give you the exact theorem. So what you do is, okay, we already know one result. Okay, we already know one result, that is this theorem. Um, oh wait, I need to charge my laptop. Okay, so here is the how do I copy it? Oh, here. Okay. So here is the theorem, okay, which you mentioned before. if if any partition you try to do into monochromatic rectangles, okay, and it requires at least t rectangles, then the communication complexity is at least log 2t, okay, log t. Now what you do is this, okay, so now you have fooling set technique, okay. So this is a technique. Yeah, right, better. This looks horrible. Fooling set. What is a fooling set? Okay, a fooling set is a set S x cross y, strict subset of x cross y. Okay, if okay, it's called a fooling set. Is a fooling set. Okay, and if there exists a value, there exists a z. Okay, if there exists a z in 0 1 such that for all x comma y in this f of xy is equal to z, and 2 for all x1 y1 x2 y2 in S either f of x1 y2 is not equal to z, or f of x2 y1 is not equal to z. So what is actually happening here? Okay, so what you are trying to come up with is a set that looks very close to a monochromatic rectangle. Okay, come up with a set S that looks close to a monochromatic rectangle. Okay, come up with a set S that looks very close to a monochromatic rectangle. Okay, what is a monochromatic rectangle? It is some A cross B where at all of these positions in A cross B, okay, the function evaluates to a 1 or function evaluates to a 0. So then it is monochromatic. Okay, come up with such a set S that looks very close to a monochromatic rectangle. For example, here you can see for all values, okay, it is monochromatic. Okay, now it looks somewhat like a rectangle. It is a set of tuples, and at the same time it is monochromatic. All the evaluations evaluate to z there. Okay, now here is the fooling part. Okay. This is the fooling part. Now what do we know? Why is this fooling? Because we know if x comma y and x prime comma y prime belongs to a rectangle, then you know the alternative definition of rectangle, right? Then x comma y prime and x prime comma y also belongs to A cross B. And if A cross B is a monochromatic rectangle, say A cross B was monochromatic, then f of x comma y prime is equal to f of x prime comma y, which is equal to f of, because at every point in the rectangle it evaluates to the same value, either 0 or 1. right? So if it is monochromatic, then all of them will be the same. This is where the fooling happens. Okay, here, this is where the fooling has happened. That is, it looks very close to a rectangle. It looks very close to a rectangle. Okay, monochromatic also, because all of them will have to the same thing. Now, take any two tuples and then do the swap x1 comma y2 and x2 comma y1. Then either one of them will not evaluate to z. But so it means that it is not actually a rectangle, because if it was a rectangle and it was monochromatic, then it would have evaluated the same thing, z all over. But it did not do that. At least one of these points where it got swapped, it got changed. Now now you can see that this is where it fools. Now why does it fool? Now why does it fool? Okay, why does it fool? Why does S fool? Okay, fool us into thinking that it is a rectangle. Or what is the advantage is that um, any monochromatic rectangle okay because there is okay I won't explain why, but you'll understand. Any monochromatic rectangle contains at most one element from S. Now I think you can even complete the proof from here. This is a claim. Any monochromatic rectangle contains at most one element from S. If you had a monochromatic rectangle, okay, if you had a monochromatic rectangle and it contained, let's say, two elements from S, then what is the problem? If it contained two elements, and let me say those two elements was x1 y1 and x2 y2, then either this would be violated. I mean, either x1 comma y2 would not evaluate to z, or x2 comma y1 would not evaluate to z, or both would not evaluate to z, which violates the definition of a monochromatic rectangle, right? So now any monochromatic, that's why any monochromatic rectangle contains at most one element from S. Okay, and now if any monochromatic rectangle contains at most one element from S, the number of monochromatic rectangles is at least the size of S, right? And now what do we know? We know that the number of monochromatic rectangles is a lower bound on number of monochromatic rectangles is a lower bound for the communication complexity of the function, right? Now where was I? Okay, so number of more forms a lower bound. So now what do you have? We have this particular result that if f, okay, I'll call it theorem, if f has a fooling set S of size t, suppose it has a fooling set of size t, then d of f, this means we already know that d of f is log of number of monochromatic rectangles, right? Monochromatic rectangles, and this is already at least size t, we already saw just now. This is already at least the size of the fooling set, which is t for us. So this is t, nothing but t, so I'll rewrite it log of t. Okay, so this is another way to do it. So what is the strategy to prove a lower bound? Okay, come up with a large fooling set, say something like 2 to the n cross 2 to the n. Okay, come up with a large fooling set. Okay, and that's it. Actually, if you come up with a large fooling set, say 2 to the n cross 2 to the n, then you already have this log of 2 to the n, which will prove the n bound. Okay, no, not 2 to the, okay, it's, come with large Boolean set 2 to the n, just not 2 to the n to the cross 2 to the n. Okay, so if you come up with a 2 to the n size Boolean set, then you can always prove a linear lower bound. Okay, and this strategy can be applied so many places. I'll show you an example. Okay, so you did an example of equality. I'm not sure whether the fooling set was used for equality or not. Anyhow, I'll show it and I'll leave it to you to try the next question. Okay. So Alice and Bob each hold an n-bit string. Okay, we already know equality. I don't need to define it. Okay. Alice, Bob hold x, y, and you need to check whether x is equal to y. Use the fooling set method to show that DEQ is equal to n plus 1. First of all, we already know that DEQ is at most n plus 1, trivially. Right? Now what we want to do is need DEQ is at least n plus 1. Okay. So now how do you do that? So here is how you do it. Okay. You want to come up with a large fooling set. Okay. What is the first property of the fooling set? All the evaluation of the function for all these indices should be 1. So fooling set, okay, set S should be a strict subset of x cross y. Okay, should be a strict subset of x cross y. And so it is consisting of tuples S equals x1, x2, y1, x2, y2, and so on, xk, yk. And for this also, my function should evaluate 1. For this also, function should evaluate 1. For this also, function should evaluate 1 or 0. But for all, it should be 0, or for all, it should be 1. So, and what is the function? Equality, which means that x1 is equal to y1, x2 is equal to y2, and so on. So f evaluates to 1 in all of these. So I'll rather write S as all alpha comma alpha such that alpha is in 0, 1 to the n. Okay, now my claim is this is a fooling set. Okay, now claim S is a fooling set. Let's just check that. Okay, let's check that. And what is the size of S? What is the size of S? How many tuples are there?
2 power n.
Exactly. Good. Next thing is that size of S is 2 power n. Okay, good. Now S is a fooling set, that is a claim. Now what is the first condition of a fooling set? My function should evaluate to the same value. There should exist a z such that my function evaluates to z for all of them. So for me that z is 1 here, right? So for all I, okay, in, okay, not for I, for all x comma y in my set S, okay, f of x comma y is equal to 1. This is true. For me, what is f? F is equal to, okay, since I took alpha comma alpha. Okay, good. Next, now I have a problem. I mean, which is good for us. That is the fooling part. Okay, I'll say that this is not actually a monochromatic rectangle. I fooled you. So the monochromaticity should be validated here. Sorry, the rectangle property should be validated here. Take any x1 comma y1 Okay, but this is nothing but alpha and alpha. No? So take alpha and alpha. Okay, first let me write the problem. Take x1, y1, x2, y2. Okay, either x1 um, comma y2, f of which is eq for us, eq of x1 should be 0, or eq of x2 comma y1 should be 0, okay, or not equal to 1, whatever. Not equal to 1, not equal to 1. Then it will be a full set, or both, of course. Okay, now, wait. Okay, right. Now take these two values in S, and they are nothing but alpha alpha and beta beta, or you can take it as alpha 1 alpha 1, alpha 2 alpha 2. Okay, and here it will be alpha 1 alpha 2 and alpha 2 alpha. Now obviously alpha and alpha 1 and alpha 2 are not the same, right? Because we took two different tuples. Okay, they are not the same. Okay, and if we check equality between alpha 1 and alpha 2, of course I'll get no on both of them. Now we know that this is a fooling set. This part is proved. This is a fooling set. And next part is that S is equal to 2 par n. Right. Now we are going to use the theorem. Using theorem, what do we know? That D of equality is at least equal to n. I mean log of log of 2 to the n, the size of S. Okay. Now which will be 2 to the n, so this is n. So now what do we have? D of equality is between n and n plus 1. Right. How do we make it tight? How to make D of equality is equal to n plus 1? So simple argument. Okay. How to make D of equality equal to n plus 1? Simple argument. Okay. So simple combinatorial argument is that you have this matrix for equality. And what does matrix for equality look like? It looks something like this. There are 0 entries here. For a non-trivial x and y, I mean, unless x and y are of bit length 1, there will always exist, okay, there will always exist a 0 somewhere in the matrix. There will always exist a 0 somewhere in the matrix. Yeah, actually, there will exist multiple zeros, but at least one 0 is enough for us. So for n greater than 1, okay, there always exists a 0. There always exists a 0 in um, in the matrix. Okay, if there exists at least one 0, what does it mean? There are at least one monochromatic rectangle. Remember, monochromatic means that it is either all zeros or all ones. So we already said that, okay, there are several monochromatic rectangles of color 1. Okay, but what about monochromatic rectangles of color 0? There is at least one 0 in the matrix. So to cover this 0, you need at least one rectangle, right? So therefore there exists at least one monochromatic rectangle for 0, covering 0. covering 0, or monochromatic, or you can say of color 0. There exists at least one monochromatic rectangle of color 0. Okay, so how many total monochromatic rectangles? Number of total monochromatic rectangles is at least the number of monochromatic rectangles for 1 and number of monochromatic rectangles for 0. Okay, and for the first one, it is at least the size of the fooling set, which is size of S, and for the other one, okay, it is 1, exactly 1. Actually, for the so we can directly apply it to the first one. Log of size of S plus 1, which is at least equal to log of 2 to the n plus 1, which is at least equal to n plus 1. Okay, because we already said that since S many monochromatic rectangles are there, you'll need at least S many size as many elements in the fooling set are there, you need at least log of as many monochromatic rectangles to cover it. Okay, number of, this is the number of one monochromatic rectangles, and this is the number of 0 monochromatic rectangles. Okay, and that is the end. That is how you can prove that d of eq equals n. So is this clear, Suraj?
Sir, what if we have just one bit information?
Yeah, if there is just one bit of information, if there is just one bit of information, this for a lot of theorems in complexity theory, okay, we do not mention this phrase, okay, for a large enough n. We generally ignore this, but let's say you want to look at that case also, that let's say n is equal to 1. Okay, Alice is holding one bit A and Bob is holding one bit B. Now you can apply the adversarial approach without any loopholes. Now obviously they need to communicate with each other, and the best way that Alice either of them needs to send at least one bit. So the most obvious way to do it would be Alice would send one bit. Alice would send one bit. Okay, and now Alice has sent one bit, and let's say it sent itself. It needs to send itself. And what should Bob do? Bob will compare A equals B. Okay, Bob will compare A equals B. So now, if he says yes, then he'll send a 1 here, and Alice will come to know, and Bob will come to know. Both will come to know. Or what they could also do was Bob could send a B also, and Alice would check on her side, and then both would come to know. But you can see that this requires at least 2 bits, which is n plus 1. Now, for such a specialized case, this is what is called an adversarial approach. Okay, adversarial approach is your enemy works in some way, okay, and you're trying to beat your enemy. That is the strategy, but that strategy does not always work. For example, to prove for a general equality algorithm, to say that any protocol must behave this way given any adversary, that you cannot do. But here, the adversary can only work in very few number of ways. It can only send one bit, right? So here, this adversarial approach will work, and you can say that, oh, okay, well, in the case of n equals 1, when n equals 1, the at least 2 bits need to be set. So again, n plus 1 is preserved. But even let's say this was not the case, but there is nothing, no harm done, because a lot of times in complexity theory we don't mention this for a large enough n. Okay, we are more interested in if something is true for a large enough n, and which is a constant, okay, n is greater than c, then we usually don't mention this at all. You may have seen this in things like time hierarchy theorem and stuff like that, where you don't mention these kind of details. But in this case, it looks like Alice and Bob still needs to send two bits. One bit is not enough for both of them to know. Is that clear? Or even
Yes.
yeah, or even maybe you can do like a contradiction approach. Let's say Alice and Bob do not send two bits. Let's say they send at most one bit. Then you can say that either Alice sends one bit or Bob sends one bit. Then let's say Alice sends one bit. Okay, Alice sent one bit. Now, how does Alice know what bit she has? Let's say she had, now you can do proof by cases. Let's say Alice thinks that the answer is yes, but what if it did not match in Bob's side? Let's say Alice had said no, but what if the answer did not match in Bob's side? And then you proved that, okay, um, you can do a proof by contradiction also, which is actually a more robust method to do this instead of this adversarial approach. Okay, but yeah, I mean, it holds in the case of n equals 1 also. So the it's not violated. Yeah, is that clear, Suraj?
Yes.
Okay, good. Um, okay, so this, try this one. Okay, then we'll stop, I guess. Um, yeah, try this question.
Sir, why it is x equal to 1 and greater
Okay.
than
Sorry. I modified into the same question. So Yeah. Suraj, any idea? So I'll give you a hint. Okay. Monochromatic. See, you want the um, Fooling set to look monochromatic, right? Now, monochromatic means that you can either set it to zeros or ones. Monochromatic means that either all are zero or all are ones. So previously on equality, what we did was we make sure that our Fooling set all evaluate to one. Try here to evaluate to zero actually. A Fooling set that was, yeah.
So then in that case, fooling set size will be 2 की power n.
Yeah, 2 to the power n is the best for us, right? In what case?
And if you take zeros,
Yeah, take zeros here this time. I'm saying. Okay. By zero, I mean let your Fooling set evaluate to zero somehow. Should I tell?
so what I thought is that
Uh,
more than half of the rectangle will be diagonally will be 0,
okay.
and then we can count the uh, uh, that borderline zeros
Okay.
just above the diagonal.
Right.
So it will be 2 की power n, and now I am not able to get how I will get one extra one.
Yeah, but to get an extra one, you can just argue for the ones. No, I mean, I get what you are saying. Okay. So you are saying you take the communication matrix and greater than looks something like this, right?
Yes, sir.
So you said there are 2 to the n many um, ones here.
Yes,
Sorry, in each row there are 2 to the n many ones at least, and each of them will require their own rectangle, monochromatic rectangle, and so then it will be n many um, n as sorry n many monochromatic rectangles, and so what I'm saying is that plus one, for that plus one, you can always argue that, oh, okay, there will always be at least one zero here. This is true, even true for n equals one case this time. If n is equal to one, you get at least one zero, but you don't get a one. Yeah. Anyway, uh, you
Sir,
right, and then you need at least one rectangle to cover this.
sir, can we use diagonal one as fooling set?
Exactly. Yeah, yeah. I was about to. Right. Good. Good. So, what is your fooling set? Fooling set is the diagonal, right? S is x comma x such that x is in 0, 1 to 10. Right. You took the diagonal. Now, let's verify the measures of fooling set. Firstly, a fooling set should look monochromatic. Okay. That is f of x comma x is equal to how much for greater than, this is greater than, right? X is greater than x, that is false for any x. Secondly, so it is monochromatic. Secondly, the rectangle property should be violated. That is x comma y and x1 comma y1, x2 comma y2, okay, are two tuples in the set. But what are x1 and x1 comma y2 and f of x comma y2 or f of x2 comma y1 should evaluate to opposite of 0, that is 1. Right, this is what we need to this is the second property. And what is here? X1 comma x1, because we took the diagonal, and this will be y1 y2 comma y2, again because we took the diagonal, and here x and here x y2 comma y1 comma y actually x2 comma x2 comma x2. So here x1 comma x2 and here x2 comma x1. Right? Now if you have two integers which are distinct, it should be true that if you have two natural numbers, okay, if you have two natural numbers which are distinct, x1 is not equal to x2, and you have them, and it should be true that one of them should be greater than the other, right? So either this is true or this is true. If this is false, then this must be true. If this is false, then this must be true. Getting it? Suraj? Hello?
Yes, sir. Yes, sir.
Right. So now this property is true. So this now is this is a fooling set. Okay. Therefore S is a fooling set. But this is not enough. We want to find the size of S. Now what is the size of S?
Two की power n.
Right. So number of zero monochromatic rectangles, okay, is at least 2 to the n. Sorry, at least log of 2 to the n. And number of one rectangles Now you can argue that, okay, for a large enough n, that is for an n which is greater than 1, okay, number is at least 1 for n is greater than 1. So therefore, what is the communication complexity of greater than? It is n plus 1, at least n plus 1, which implies it is exactly equal to n plus 1. Okay, clear?
Yes, sir.
Okay, great. Okay, so we'll do that much for this time. Okay. I noticed that there is also a subjective question for the NPTL. So in the assignment, there are two parts to the. There are two assignments. Okay, for this week. One is the MCQ and the other is subjective. So in the subjective one, try to write it in a clear, concise way. Okay, that is what I would recommend, because in MCQ it is straightforward that you just put it there. Okay, you put the answer and then you get the marks, right. In subjective, well, it's in the name. It is subjective what the examiner sees. So there, I recommend that you write your answers clearly, step by step, so that everything comes out properly. Okay, and try to keep it a bit formal. So yeah, that is it. So yeah, again a reminder: there will be a second session. There will be an extra session. There will be a last week 12 session on the next Tuesday, and on Wednesday 4 p.m. there will be the extra session for 1 hour only. Okay, and yeah, that one I recommend you to please attend that. Okay, and so yeah, that is it. Okay, and do you have any questions? Then we can stay and discuss. Otherwise, we can call it a day. Okay.
Sir, that independent set and that click, sir, can you summarize in short?
Sure. Okay. Quickly, I'll summarize it. Okay. And if you want, I can explain it again next time also clearly. So what you want to do is, Alice is given a click. Okay. Alice is given a click, and Bob is given a independent set, which means they don't have vertices between them. And there is a graph. Okay, and you want to check whether there is a vertex V which is common between Alice and Bob. Okay. So now what Alice could do is, okay, send all the vertices in her click. And how much space, how many bits does it represent to represent every vertex? Log n many, right? If there are n many vertices, then log n many. But in the worst case, the click may be of size n, order n. Then you'll be sending n log n many bits. That is too much, and that is too much, right? So you cannot do that, and you want to do something better. So okay, fine, you can send these vertices there, but you want to send them in a more clever way. What you do is you take advantage of degree. Now, what you do is Alice picks a vertex, picks a degree which is checks if there is a vertex of degree which is less than n by 2. Okay. Okay, fine. We located it. What is V as degree of degree less than n by 2? Now, what if there was no vertex of degree n by 2? That is another question. Right. Then Alice sends the bottom symbol. There is no vertex of degree n by 2. Bob asks now whether there is a vertex of degree n by 2 in G. Let's say Bob had a vertex with degree n by 2. Then clearly the answer is no, because Alice had no vertex of degree n by 2, while Bob has a vertex of degree n by 2. Then how can there be a common vertex? Because each vertex here has a degree greater than n by less than n by 2. Then in the original graph, okay, in the original graph, then there should be that same vertex should appear here also if they had something in common, but that is not the case. So you already see here that we need these bounds matching between them. Okay, if Alice says, and if they have a vertex in common, if Alice says there is a vertex of degree at most n by 2, then Bob should also say yes, there is a vertex of degree at most n by 2, and so on and so forth. Now, what the next step is, you want to reduce the size of the graph. Okay. In the first case, you are blowing up. Okay. So first, what you do is, now you ask whether there is a vertex of degree at most n by 2, and yes, you found it. Let's say, and this vertex V has such a case. Fine. Then you'll send vertex V there. You'll say yes, there is a vertex, and you'll send the vertex there. And Bob can of course match whether that vertex is there in his one also or not, but it's okay. He has got okay. He what he does is, he checks if there are. He also wants to check whether there is a vertex with degree n by 2, less than n by 2. What he does is, he checks whether there are non-neighbors of degree greater than n by 2, which is the same thing, but now he's talking about non-neighbors. Okay. Now, are we losing any information here? First of all, no. Why? Because Alice has a vertex V. Okay, and the fact that she sent all of V's neighbors means that since the clique, okay, everything in the clique is also V's neighbors, so obviously she'll be sending. Obviously, so not sending, the new set that she considers will contain the original graph also. Now, now both are prepared. Okay, now both have a potential set of same degrees. Okay, and we are not losing any vertices on the way. Now what we do is, Alice reduces the size. Okay, she checks whether n less than n by 4 is there. Now there are fewer vertices of n by 4. Okay, and sure, then Alice says, okay, fine, I have a vertex of less than n by 4, and sends it to Bob. Okay, and Bob also asks him the same thing. Now, are we again losing anything here? No, because again, if there's a vertex with n by 4 or lesser degree, okay, all the vertices are still connected. Okay, with Alice, and all the vertices in Bob's side are still connected. I mean, still disconnected in that case, right? And again, now you keep doing this process. You keep doing this process, and you keep reducing the size. Finally, you'll come to a point, okay, where the degrees should match, or the degrees, or you cannot find them. Okay, either the degree matches, okay, or you cannot find them. Now, if you cannot find them, okay, what happens if you cannot find them? If you cannot find them at all, then on either side, then it means that no, they don't have a common vertex, because if they had a common vertex, then the degree thing should match. Right. Just a moment. Okay. Yeah. So. Oh, okay. Yeah. So where was I? Okay, and you keep doing this process. Okay, and finally you either end up with zero vertex or one vertex. And if you end up with one vertex, okay, if you end up with one vertex, well and good. You cannot end up with two or more vertices, because like we argued that if you have two vertices that belong to a clique also, an independent set also, it does not make sense, because there is an edge between them. Okay, but how many rounds does it take? Well, it takes log n round, because you're doing binary search. Okay, and in each of the log n rounds, what you are doing is you're sending log n many bits, and then it will take some log square n many. So is that clear? But if it is not clear, then I'll explain it again next time. Okay, in the beginning of next time. Yes, Suraj?
Yes, it's clear now.
It's clear? Okay. Okay then. Sure. If you have any more questions, then we'll discuss. Else,
No, sir.
Okay. Sure. Then see you next week, Suraj. Okay.
Thank you, sir.
Okay, thank you. Okay.